Good morning, afternoon, or evening to folks tuning in from around the world. As is tradition, why don't you let us know where you're tuning in from? Welcome to the Qiskit Quantum Seminar. And just a reminder that the seminar takes place every Friday at noon Eastern Time and will be hosted on the Qiskit YouTube channel. You can always subscribe to go back and catch up on anything you missed, but you can only ask questions here live now during the seminar. I'm Derek Wong, a research scientist at IBM Quantum, and I'll be your host today. And of course, there's a lot of care and effort that goes into these seminars, so I'd also like to thank our producer, Zlatko Manev, video producer, Paul Searle, and managing producer, Olivia Lance. All right, so today we'll be hearing a talk by Ashley Montanaro, who will speak about near-term quantum algorithms for optimization. Ashley specializes in quantum algorithms and quantum computational complexity. He holds a PhD in quantum computing from the University of Bristol, did a postdoc at the University of Cambridge, and is now professor of quantum computation at Bristol. He is a founding editor of the journal Quantum and co-founder and CEO of Phasecraft, a quantum software startup whose goal is to make the most out of near-term quantum computers. Take it away, Ashley.
Hi, everyone. Thanks for tuning in, and it's fantastic to be here. Today I'd like to tell you something about near-term quantum algorithms. So what I mean by this is the kind of quantum algorithms that you might run on a quantum computer in the relative near future, not necessarily today, but in the next few years, as opposed to the next 10 years, 20 years, or even 30 years. And there's a sort of very big and interesting question, which is, what can we hope to do with these near-term quantum computers? What can we do in the next few years with the sort of quantum machines that are being developed by quantum hardware companies all over the world? And there are a few really interesting candidates for this. One example, which is really nice, is modeling quantum systems. So simulating and modeling the quantum mechanical systems that occur in nature. And a reason why this is very interesting is that actually many really important physical systems for practical applications actually need an accurate understanding of quantum mechanics to model them correctly. So this might include batteries, solar cells, maybe catalysts. All of these are important systems where quantum mechanics plays a crucial role. And this is a very interesting direction which many people have worked on, including ourselves at Phasecraft. I'm just giving you one little citation there. Just came out. You could look at if you're interested. So there's many exciting applications of quantum computers in quantum simulation and material science in particular. But another really interesting direction is actually solving hard problems that come from the domains of constraint satisfaction and optimization. So what I mean by this is problems where we have to search over many different possible solutions to try to find the best solution. So this might be the solution that satisfies some constraints which are difficult to satisfy altogether, or it might be a solution which is the best one, the one that minimizes some cost or maximizes some sort of value. And problems like this are everywhere in science and engineering. Some particular application areas where these sorts of problems occur include logistics. So, for example, efficient shipping, placement of facilities, timetabling, design of electronic circuits, computational finance, and many, many more. And this is another area where near-term quantum computers may play an important role. And this is what I'd like to talk about today. And I'm going to be talking about the potential for near-term quantum algorithms to address optimization and constraint satisfaction problems in two particular cases. The first of these cases is a really, I guess I would say, quite famous and fundamental problem in computer science, which is known as boolean satisfiability. So this is a very sort of mathematical looking problem, which I'm just going to define for you sort of briefly here. And it consists of finding a solution to a set of constraints on Boolean variables. So what do I mean by a Boolean variable? It's something that can be either true or false, also 1 or 0, on or off. And we have n of these variables, which I'm usually going to call x1 through xn. And we also have some constraints on them. And I've shown an instance of such a Boolean satisfiability problem on the slide here. And this is some constraints where the constraints are in these brackets. And the first one is the constraint that x1 has to be true, or x2 has to be true. So this V symbol means or x3 has to be true. So this clause, so-called clause here, this constraint, says that at least one of x1, x2, and x3 all have to be true. And then this this wedge symbol here in the middle, this represents a logical and. So it says that we want this clause to be satisfied, and this clause to be satisfied, and then this second one here, sorry, means that we want this one to be satisfied as well. And this symbol here means not. So this is saying that this second constraint is satisfied if x1 is false, or x4 is true, or x7 is true. So we want to satisfy this one, and then this also satisfy this third one here, which says that x2 has to be true, or x5 has to be false, or x7 has to be false. So to think about problems of this form, we normally have many of these clauses. We have many variables, we have many clauses on those variables, and we want to satisfy them all at once. And even though each individual one is easy to satisfy, put them all together and they may be actually very hard to satisfy. In this case, we can satisfy all of them by setting all of the variables x1 through x7 to be true. But in many other cases, it's much more challenging to see if you can do this. And in fact, this problem is a prototypical example of problems that are so-called NP-complete, which means that we don't think that there's actually any efficient classical or even quantum algorithm for solving them. But even though we think that the best algorithms are going to run in time exponential in the problem size, we can still try to get this exponential complexity down as much as we possibly can. We can try to solve problems which are as large as possible in as short a time as possible. And this problem turns out to be very important in practice. So people have spent a lot of time actually trying to get their algorithms as efficient as possible for solving it. And today I'm going to be talking about a special case of this problem, which is called random k-sat. So sat obviously short for satisfiability. And in this special case, we assume that each of these clauses, each of these constraints has k variables within it. So here k could be equal to 3. And we're also going to assume that each of the clauses is actually chosen at random. So the variables in it are picked at random from the n variables that we're allowed to use. And whether they have a not in front of them or not is also picked uniformly at random. So with 50% probability, each variable has a not in front of it. And instances like this are not necessarily useful for practical applications, but they're a fantastic benchmark to understand how well different algorithms can perform at solving the satisfiability problem. And today I'm going to be talking about how well near-term quantum algorithms might do for solving this problem and how they might compare against classical algorithms. And towards the end of the talk, I'll mention a very different looking problem, but one which also fits into this world of optimization and constraint satisfaction. And this is the problem of protein folding. So in this problem, we're looking to predict the 3D structure of a protein given a sequence of amino acids. So the amino acids you can think of as basically a string specifying the atoms that are in a protein. And what we're interested in understanding is how this protein looks when it ends up folding itself into a 3D structure. And the way that it looks actually determines its function and how it behaves. So this is very important for practical applications in bioscience. And this turns out to also be a computational optimization problem that we can address using classical or quantum algorithms. And here what I'm going to be discussing is how well we might expect near-term quantum algorithms to perform for this problem based on some analysis of small-scale examples of this. And one other nice abstraction of this problem, which I'm not going to discuss today, but I'll give you a reference at the end, which you can look at if you'd like to learn more, is that we can abstract away a lot of the biology and a lot of the complexity of this problem and think of it in terms of a mathematical problem called generating so-called self-avoiding walks. So this is basically another example of a sort of 1D structure that can be represented in 2D or 3D. and it has some sort of interesting mathematical aspects, and it becomes a sort of nice model for understanding the performance of a quantum algorithm. But as I say, I'm not going to discuss this today, but the paper that I'll cite at the end has more about this. So I'm going to be talking about these two different directions today. I should mention that everything I talk about today is joint work. The first of these results is joint work with Sami Bulebnan, who's a PhD student working with me. And the second of these results on protein folding is also joint work with Sami, and is also joint work with a team at Roche who are experts in the bioinformatics and bioscience aspects of this. Okay, so I'm going to get going by talking first about the quantum algorithm approach that we're going to be studying for addressing these problems. So the algorithm that we're going to be looking at is known as the quantum approximate optimization algorithm, aka QAOA. And this is an algorithm that may be familiar to many of you on this call who are interested in quantum computing. In fact, many of you may have implemented this algorithm yourself and maybe run it on real quantum hardware in the cloud. And it's actually a very sort of prominent and popular algorithm for trying to solve optimization problems using near-term quantum computers. Its genesis actually goes back to wonderful work by Tad Hogg back in 2000, but it was really popularized and extended by Ed Fahy and co-authors in 2014. And since then, it's become a really really interesting and fruitful domain to look at the potential for quantum computers to outperform classical ones. And the way that this quantum algorithm looks is that we represent it in terms of a quantum circuit like this on the screen. And we start out with a number of qubits, where the number of qubits actually sort of corresponds to the number of variables in the optimization or constraint satisfaction problem we're trying to solve. Each qubit starts out in this plus state, so it's a superposition of 0 and 1, equal superposition of 0 and 1. Then we go through a number of different operations in the quantum circuit. First, we have an operation which depends on a certain cost function, and I'll show you a bit more what this looks like mathematically on the next slide. But basically, this is something that depends on the problem that you're wanting to solve. Then we have a so-called mixer part, where we have some quantum gates which only act on one qubit each, which can be seen as a sort of rotation which goes into a different basis and sort of does some interesting sort of quantum superposition and interference effects. Then we have another layer that depends on the problem, then this layer of X rotations, and then so on. We have multiple layers like this. And then in the end, we measure and we get some answer. And we might potentially run many times in order to get a good answer to the problem that we want to solve. And one interesting point about this algorithm is that it depends on a number of parameters, which I've called gamma 1, beta 1, gamma 2, beta 2, gamma 3, beta 3 here. And these parameters are not obvious in advance. They can either be optimized, perhaps using the quantum computer itself for a given problem, or they can be chosen in advance based on some knowledge of the problem class that you're looking at. And in this work, we're going to be actually looking at both of these possibilities. So one thing that's very appealing about this algorithm is that it's quite easy to code up on a quantum computer. The operations in it are not really that complicated. And there is some evidence that it can do well on hard optimization problems, though it's fair to say that at the moment there's very limited theoretical evidence that it can actually outperform classical methods, although I'll talk about some further evidence of this form today. And in order to understand its performance, in general, it's actually necessary to simulate it numerically, or in fact even run it on a real quantum computer. Okay, so how does this QAOA algorithm look mathematically? So basically what I've written here is just a mathematical form of what I had on the previous slide. So we're starting out with this quantum state, which is a uniform superposition over all possible bit strings on n bits. Then we are alternating these operations, which we can think of as time evolution according to different quantum Hamiltonians. The first one of these, HC, is actually a sort of diagonal Hamiltonian. It's one which is like a classical looking thing. And it's expressed in terms of some cost function C, where basically this function C, for a given string of bits, it returns what the cost is of that string of bits. So this at the moment is a sort of abstract thing, and we'll make this a little bit more concrete in a minute. But basically, we can think of this as any function which, for each bit string, tells us what the cost of that is, and we're trying to sort of minimize this cost over bit strings. So that's this HC part. Then there's also this HB part, which is this rotation within the x-axis on each qubit. And we repeat these steps one after the other until we get to the end. And we have this parameter p, which is the number of layers in the algorithm. So QAOA has a number of layers within it, and I'm normally going to use p for the number of layers there. And we're going to use this notation psi QAOA for the final state that we get at the end of the algorithm. Okay, so right at the end of the algorithm, we just measure in the computational basis, we measure each of the qubits to get a candidate solution to the optimization or constraint satisfaction problem we're trying to solve. And as I mentioned, this is a so-called variational quantum algorithm. So these parameters beta and gamma need to be determined. So we can either determine them in advance or we can optimize them in some way. Okay, so that's the structure of the algorithm that we're going to be looking at. And now we're going to look at how we can apply this to the problem of KSAT, to this particular, nice problem of Boolean satisfiability. And here we have a particular cost function C, which is the number of violated clauses. So what do I mean by this? I mean the number of clauses which are not satisfied by a given bit string. So we can think of a problem instance in terms of, we can write it in terms of, we can call it sigma, into where we have some clauses sigma 0 through sigma m minus 1. So we have m clauses in our instance. So here, for example, m would be equal to 3 in this example. And then we have a cost function, which depends on sigma. And it's basically the number of clauses that are not satisfied by some assignment z. So if we look at this example at the top here, if I have the assignment that's all true, then C of 111 or C of true, C of all trues would be equal to 0 because we would satisfy all of the clauses. Whereas if I had a assignment which was of the form, true, 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 false, 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 then sorry, no, I said the other way around. False, 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 true, 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 true. This would have cost of 1 because we would not satisfy the first of the clauses, but we would satisfy the other ones. So it's just the number of clauses that are not satisfied by a given assignment is the cost. And then we have this corresponding diagonal matrix, a so-called Hamiltonian, depending on the formula, which is just the big sort of matrix where we have each diagonal entry within it is given by the cost of the corresponding bit string. So then the QAOA algorithm depends on this this cost and this diagonal Hamiltonian. Okay, so one thing that we're going to do in this work, which is a bit different to what people often do in QAOA, is that we're wanting to actually maximize the probability of finding a satisfying assignment. So we're wanting to maximize what we're going to call the success probability, which is the probability that the algorithm returns something, which is a bit string that actually satisfies all of the clauses. So in some cases, maybe there is no bit string that satisfies all of the clauses. Maybe somehow there's a contradiction and we're not able to satisfy them all simultaneously. But today we're always going to be thinking about instances that we can satisfy. And even then, for instances like this, it can be very hard to actually find a satisfying assignment. And what we're trying to do is we're going to try to maximize the probability of finding such a satisfying assignment to the variable, maximize the probability that QAOA returns something that satisfies all of the clauses. And this is a bit different to what people often do, because often in QAOA, people try to optimize the so-called energy, optimize the number of clauses that are satisfied. And this may give you something slightly different, because maybe the sort of optimal expected number of clauses that you satisfy is actually different. The parameters that optimize that are different to the parameters that optimize the success probability. And okay, how are we going to do this? Well, what we're going to be doing is we're going to be looking at this this random KSAT problem. And how are we going to find good parameters for this? Well, one way we could do this is actually just looking at small instances and hoping that the parameters scale up to larger instances. So for small size instances of random KSAT, we can generate them computationally, and we can test, we can do this optimization on a standard classical computer. We don't have to use a quantum computer if we have small problem sizes. And so we can hope to optimize these parameters numerically, and then we can hope perhaps to analyze how well QAOA does with those parameters as we scale up to larger sizes. But how do we do this analysis of scaling up to larger sizes? And this is, I guess, is the biggest challenge that we face, and this is the main result in our work, I would say. Basically, we're able to come up with a theoretical result that actually calculates for large problem sizes for a given set of parameters what is the expected success probability of QAOA applied to random KSAT. So I'm just going to unpack all of the words on this slides a bit. So we're considering random instances of this KSAT problem, so random boolean satisfiability instances with k variables per clause. And we have an expected number of clauses m, which is equal to r times by n for some constant r. So this is a parameter that we would fix in advance. And then what we show is that for some fixed parameters beta and gamma, and for some choice of k, and in fact in this work we will have to assume that k is a power of 2, though this isn't a particularly significant restriction, and actually we have removed it since then. Then for sufficiently small gamma, but this is just a technical restriction, and in fact, this sufficiently small thing is independent of the instance size, so this turns out not to be a significant issue, but anyway, it's a technical issue of our results. Then what we're able to show is that if we look at the expected success probability for over random KSAT instances, so this is random instances of the Boolean satisfiability that are generated with a certain number of clauses, which has expected number m equals r times by n, and we're picking random instances like that, and we're looking at the expected success probability over those random instances with these parameters, and we are then taking the log of that, and then we're dividing by n. Then we show that this limiting value exists, and also you can compute it via some numerical procedure which depends on some variables where there's exponential in p of them. So okay, so the key point of this is that the complexity of computing this thing, this number here, does not depend on n. So we can take the number of variables n to be very large, it goes to infinity, and we show that we can compute what this thing is. And basically what this is the runtime of the algorithm is of the form, or sorry, the success probability, I should say, of the algorithm is of the form 2 to the minus alpha times by n for some alpha. And this result says we can compute what alpha is as n goes to infinity. So basically we can compute what the scaling is of QAOA's success probability. And the success probability determines what the runtime is of QAOA. So basically this enables us to bound how well QAOA performs. So this this enables us to get a sort of theoretical handle on what the scaling of QAOA should look like for these random instances of this KSAT problem. So the hope is that then we can use this sort of scaling estimate to compare QAOA with classical algorithms. And of course, another interesting point is that this scaling exponent, this number here, we can also use this as a way of optimizing the success probability over beta and gamma. Basically, this is some function that we can compute classically, and we can use this to work out what the best beta and gamma actually are. So this is an alternative way of doing this compared with what I suggested on the previous slide, which is looking at small problem sizes and computing the best beta and gamma and hoping that they scale up. We can also use this method on this slide too. Okay, so this is a theoretical result on the performance of QAOA, and an important point first is that we should check that this actually matches the empirical performance that we see. So, okay, so I should say what's going on this graph. So this is fixing a particular choice of k. So k equals 8. So this is solving random 8-SAT problems. And this is looking at different instance sizes, so a different number of variables. And the number of variables is n. And in these numerical experiments, we were taking n being between 12 and 20. And what we are comparing here is the mean success probability of QAOA taken over different n's. So yeah, taken over different n's here and different choices of p. So this is different numbers of layers of the algorithm. And we were firstly looking at our theoretical results, which are the dashed lines here that we can see. And these theoretical results, like they tell us what the scaling is of QAOA as n goes to infinity. So, you know, the success probability is of the form 2 to the minus alpha times by n. And this is the theoretical result tells us what alpha is. So basically, this is just plotting the straight line based on that theoretical bound. And then we also have these solid lines, which is the results we get numerically. So this is looking at some random instances of KSAT for these different sizes. And this is applying QAOA to those instances and looking at the success probabilities that are obtained. And what we see is, firstly, we seem to have this nice sort of exponential decay of the success probability in both cases. So this is a log plot. So these straight lines mean that the success probability seems to be going down exponentially. And also importantly, we have a very nice matchup between the theoretical predictions, which remember only hold as n goes to infinity, and the numerical results that we get. So the theoretical results actually, they don't say anything about the sort of constant factor in front of the scaling of the probability. So on this sort of log plot, that corresponds to a shift in the y direction. So we wouldn't necessarily expect actually that the lines precisely line up one on top of the other, but we actually do see that as well as the slope being correct, that in several of these cases, actually even the constant factor in front seems to have worked out pretty well, which is very nice. And I guess I should also mention, like, what were the QAOA parameters used for these points? So in each case, we choose optimized QAOA parameters. This is these betas and gammas for given n based on averaging over over some random instances. So this is choosing some good parameters and then using the same parameters in both the theoretical bound and the numerics. Okay, so basically these results give us some confidence that theoretical predictions actually match up with the numerics. And then the next thing that we did was actually look at the just benchmarking the performance of QAOA. So basically these the previous results sort of give us some sort of indication that, you know, our theory matches up with experiment. And now what we were interested in doing was actually experimentally comparing the performance of QAOA versus classical SAT solvers. And we looked at a number of different solvers for SAT instances. This is something a problem that's been really worked on a lot classically. There are entire competitions based on trying to solve satisfiability as well as we can. In our experiments, there was a particular solver called walksat-lm, which we found to perform the best for the instances we were looking at. And we compared this and a number of other solvers, a couple of which are shown on this plot. We compared this against the empirical scaling that we find for QAOA on random instances within this sort of range of still relatively small sizes, but sizes that appear to be big enough that we seem to be getting some good representation of the large instance size behavior. So we consider a few things. So we consider firstly like QAOA with 14 layers, which I've shown here because it's the point where QAOA starts to match the behavior or the performance of this walksat-lm algorithm. We also consider QAOA with a lot more layers, and we see that the performance is a bit better. We also consider QAOA, but where we actually try to even improve the results of QAOA by applying a classical optimization algorithm called walksat afterwards. And that does a little bit better as well, though not significantly better. So, what we're plotting, and these ones at the bottom here, MapleSat and Glucose-4, they're just different classical sat solvers that are quite widely used. And, what we see here is that the median running times of these different algorithms seems to again scale nicely exponentially, and we see that the scaling seems to be a bit better for some of the QAOA algorithms. And one point I'm sure some of you are wondering is, how do you compare the running time of a quantum algorithm and a classical algorithm? And indeed, this is not this is not obvious. So in the case of the classical algorithms, we are basically counting the number of computational steps in the algorithm. And in the case of the quantum algorithm, basically we are computing the success probability of QAOA of one run of QAOA on a given instance, and then we're taking the 1 over that, and then that gives us the expected time it takes QAOA to solve that particular instance. And what was that question?
Yeah, sorry, just a quick question. So this is all for the random stat type problems, right?
Mm-hmm.
What do you expect if you put some structure into how those problems are chosen in the first place?
So that's a great question, and basically we don't really know, I think it's fair to say. So the it's not, in some cases we might expect that the structure of the problem makes it easier for classical solvers. In other cases, maybe it would make it even easier for the quantum solvers. I think in this work, we were really focusing on trying to understand the scaling behavior of these different sorts of algorithms. And so for that, it's kind of difficult to find families of structured instances which will enable you to understand this. But I think it's a super interesting question.
I see. And another question is, so you compute the running time by computing the number of steps, right? Sorry, I think I missed this while thinking about my previous question.
Yeah,
but so then what happens when you take into account like the actual differences in like clock speeds, right? A gate on a superconducting device being nanoseconds, but on a proper classical device, probably picoseconds or something even faster.
Absolutely. So indeed, I think that was the very next thing I was going to say, that you do have to take this, like for a real sort of practical experiment, you would have to take this into account. So like what's important in these plots is actually not the absolute position on the y-axis, it's the scaling, right? The slope of these.
Got it.
Because, if you have one of the lines being a better slope than another, then for large enough instances, you are going to see, a time improvement. But obviously, if the lines are kind of close in slope and there's a big overhead that the quantum computer is paying, then maybe you do not see a speed up in practice.
Okay, thanks.
Cool. No, that's a great question. It's good to make sure that's clear. Okay, so what we see here is that it seems that the quantum algorithm achieves a somewhat better scaling than the best classical algorithms we tested. Although I should stress that this is not an especially large improvement at present. It's it's scaling of like to improve the classical algorithm from 2 to the 0.325n to perhaps 2 to the 0.295n. So it's not a vast improvement. But on the other hand, I think this is the first time that any result has suggested that QAOA may actually outperform classical algorithms for this kind of problem. So that's why we found it interesting. It sort of opens the door to other speedups of this nature. And I think another interesting question is, like, if we were trying to beat this walk-sat-lm algorithm, how deep a quantum algorithm will we actually need to achieve that? Like, how many layers of the algorithm will we need? Because we can see that the performance of QAOA improves as the number of layers of the quantum circuit increases. But obviously, the deeper the circuit, the harder it is to run on the quantum hardware. So what we can try to do is, using these results, actually plot the scaling with p of this scaling exponent. So this y-axis here is the constant in the exponents that we've just been discussing. So if the runtime is 2 to the alpha times by n, like this is the alpha here, and the dashed line here is the scaling that we see for walk-sat LM, which is a bit worse than 2 to the 0.3 times by n. And there's a few different ways you can try to extrapolate the performance of QAOA. You can look at our sort of theory results, which look at this is this sort of analytic curve here, this red one, where we look at the scaling exponent for as n goes to infinity. But this is the scaling in terms of the inverse probability, and so for some sort of annoying technical reason, like this does not precisely give you the median running time of the algorithm. So in fact, this red line basically gives you a lower bound on what you would expect the median running time to be. And it's a sort of interesting question of how close to this lower bound we actually are going to end up in practice. And so, what we did is, looking at our numerical results on the median running times of QAOA, we looked at the sizes that we were able to go to numerically, and then we tried to extrapolate to larger p. And there's an interesting thing that, depending on how far you look at p, like what sizes of p you look at, and the extrapolation may look more or less sort of positive for QAOA. So if we look at these points here for where we did optimization for very large p, actually the scaling exponent is only a little bit better than walk-sat-lm. So this looks somewhat negative for QAOA. But actually, there are some reasons to think, I would argue, that this is possibly overly negative. And basically, the reason is that for small, it's a somewhat technical reason, which is that for small sizes, which are the ones that we are actually able to run, are ones which we're able to optimize the QAOA parameters for small sizes, actually the problems that we're solving are kind of too easy. And the result is that we end up with QAOA sort of choosing parameters which kind of over-index on the sort of easy cases. Like, by optimizing the success probability, that's not necessarily actually a good estimate of the median running time anymore, the sort of the median success probability. And this may explain why we see less good behavior for large p, or it may be that actually the behavior of QAOA does not improve so well as p becomes large. Maybe it saturates early, and at the moment we're sort of not able, I would say, to distinguish between these two cases. It may be that the running time sort of scales like this sort of dash, this solid line here, or it may be like this something like this dashed line here, or potentially even worse. So this is an interesting direction for further work. And so what we saw in this part is that actually I would say there's some relatively promising performance of QAOA, in the sense that we end up outperforming the scaling of the best classical algorithm that we were able to test for this random KSAT problem. And in the second part of the talk, which is a bit quicker, I'm just going to talk about some results where actually it turns out the results are not quite so positive for QAOA. And the problem that we're going to be looking at is protein folding, as I mentioned. And this is really a fundamental problem in computational biology, with applications in a number of different areas. And for me as a computer scientist, I sort of think of a protein as just a sequence of amino acids, which is something that I've shown here, where we have this sort of long string of atoms and molecules that sort of looks like this, with these bonds between them. And drawn here on this slide, it's a sort of 2D kind of thing, or perhaps even a 1D sort of structure. And what we're interested in doing is understanding how this looks when it sort of folds itself in 3D, and how it looks when it produces a 3D so-called conformation. And it turns out that this is what determines the sort of biological function of the corresponding protein. And the way that this folding happens depends on the physics of the problem of, the way that the protein behaves as a sort of structure of atoms in space. And this computational problem is hard to solve. It's another problem where we're optimizing over many different possible solutions computationally, and it turns out that this is extremely challenging. And many of you may have seen that there have been some recent incredibly impressive results on protein folding using machine learning. So there is this real breakthrough, I guess, back in around 2020, which is work by the team at DeepMind called AlphaFold, which was able to predict how proteins would fold based on a lot of previously existing data. And this was incredibly impressive, has really, really nice results. However, I'm not a bioscientist, but I'm assured by some of the bioscientists that I've spoken to that this problem is not yet considered to be fully solved. And one way in which intuitively one can understand about why it might not be seen as fully solved is that a machine learning method is only somehow as good as the data that goes into it. And if we have a really surprising instance, which does something which we do not expect, which we have not seen before in our database, it may be very difficult for that machine learning method to produce the correct answer. So if we have something which really behaves unexpectedly, we would not necessarily expect the machine learning based method to predict that. So it's perhaps still interesting to try to understand protein folding from a more sort of direct physics perspective and try to effectively solve the physical equations that correspond to it producing its lowest energy configuration. So how might we try to address this on a quantum computer? So we're going to use an approach which several others have done, which is basically trying to think of a protein as a sequence of amino acids, and these amino acids live on some kind of lattice, so a discrete lattice. And in this work, we're looking at a so-called tetrahedral lattice, which is sort of shown here on the right, where we sort of assume that each of the atoms sort of lives at a sort of discrete point in this lattice. And there's a sort of physical reason why it makes sense to choose this tetrahedral lattice to do with the angles of the atomic bonds. But it's sort of worth stressing that this is really a sort of quite basic approximation. And in the classical protein folding literature, people do far more complicated things. But to represent proteins on near-term quantum computers, a sort of discretization method seems like perhaps a good way to go. Okay, so how are we going to represent a protein folding problem, and how are we going to attempt to solve it using QAOA? Well, we can represent a conformation, so a sort of configuration of a protein in 3D, by a sequence of turns on this lattice, on this tetrahedral lattice. So on the right-hand side, I've shown how this might be done on a 2D square lattice, but in fact, you can do this in a 3D tetrahedral lattice as well. It's just maybe a little more tricky to show. And so this is a way then of representing a particular configuration of the protein. And then what we want to do is understand the cost of each different configuration. And the cost of a configuration is given by a so-called potential. And there's different ones one can use, but in this work, we're using one called the so-called Leonard-Jones potential. So basically, this is saying the sort of energetic cost of a given configuration of these amino acids. And this energetic cost is based on things like which pairs of atoms don't like to be close together, roughly speaking. And this sort of weighting depends on which particular atoms we're looking at. And there's also one important point, which is that in principle, we could come up with configurations which are not physically reasonable. And one way they might be not physically reasonable is that we might have two atoms at the same position. We might have this sort of line winding round in 3D, sort of intersecting itself. And that's something we don't want to allow because it's physically meaningless. So we have a particular penalty term that penalizes these clashes that occur in this configuration. And then, when we put this together, we get a cost function where we can plug in a particular sort of conformation, a particular sort of string of terms, and then it will tell us what the cost of that is, and we want to minimize this cost. Okay, and a problem is that even for very small proteins, then actually there's too many of these turns to encode the protein on a small enough quantum computer that we could actually hope to simulate it classically. So in this work, we were looking at simulating protein folding problem classically, and we were wanting to do this sort of reasonably small size. And for physically meaningful proteins, this is very difficult. And the way that we dealt with this is that we only actually encoded part of the protein we were looking at. We were looking at this, we were looking at this example of alanine peptide, for example, and we were only encoding part of it. And then we were basically, assuming that we'd already classically minimized out the things off at the sides, these so-called side chains. So these are some particular extra degrees of freedom that we were basically giving ourselves for free the fact that we'd minimized these. So this basically just makes the problem easier for the quantum computer, just leaving the sort of physically most interesting bit in the middle. And then once we'd done this, we were able to numerically simulate QAOA and optimize these QAOA parameters and try to understand how well QAOA did at finding low energy configurations of this particular protein. So this alanine tetrapeptide one, which is what we were looking at. So this is a very small example. It fits within 20 qubits once you've done all this encoding. And there are a number of results that we came up with. I'm only going to show you a couple of them today. And the first thing we were looking at is how does the probability of producing a solution without any clashes, so this is one that's physically meaningful, how does that scale with the number of QAOA layers for this particular example that we were looking at? And the results are shown in this graph here, and the y-axis is the probability of producing a clash, and the x-axis is the number of layers of QAOA. And what we see is that if we want to have a relatively low probability of producing a clash, like maybe 1% probability, then we need to actually have quite a large number of layers. We need to have of the order of sort of 45 or 50 layers of QAOA. So, if we want to make most of the solutions that we produce physically meaningful, then we need to have quite a large number of layers, even in this very small example. And possibly a sort of an even more sort of, let's say, negative result for QAOA is we can actually compare the performance of QAOA against just randomly guessing. And that's something that we've shown here on this graph on the right, which needs a little bit of unpacking. So the x-axis is showing sort of quantiles Q. So basically this is saying parts of the QAOA distribution. So this, this x-axis is saying the best qth fraction of the QAOA distribution. So if we look at q equals 10 to the minus 3, this is saying the best 0.1% of the solutions found by QAOA. And the y-axis is basically saying the number of random guesses it would take to produce something that's in the within that fraction of the QAOA distribution, compared with the time that it would take for QAOA to do that. So, for example, if we see this this yellow line here, which is for p equals 3, we see that around 10 to the minus 3, this is a bit bigger than 6. And this says that if you want to produce something in the best 0.1% of the QAOA answers, then The time it takes QAOA to do that is about 1 over 0.1%. So this is about 10,000 runs. You have to run the QAOA algorithm 10,000 times. And this is saying that the ratio between the classical algorithm's performance and the quantum one is a bit more than 6. So you need to run the classical algorithm about 6,000 times, right? So roughly speaking, this y-axis is the penalty between QAOA and the best classical algorithm. And what we see is that in all cases, the penalty is never more than, a bit more than a factor of 6. So basically, this is saying that you can match the performance of QAOA on this particular very small, very simple protein folding problem with a classical algorithm that makes 6 or 7 times more, runs for time 6 or 7 times more. So basically, this is saying that for this sort of very small, very, very simple protein example, then actually the classical algorithm pretty much matches the performance of QAOA. It's a little bit slower. Okay, so that's everything I wanted to say. I'm sort of getting towards the end. And basically, I think the overall conclusion I'd like to make is that really the performance of near-term quantum optimization algorithms crucially depends on exactly which problems we're considering. And for random case-app problems, QAOA seems to have some kind of scaling advantage over leading classical algorithms. And in particular, it outperforms Grover's algorithm. So one thing you could try to do if you have a fault-tolerant quantum computer is just apply Grover's algorithm to random case-app instances. And it turns out that QAOA has better scaling than that. So this is perhaps the first evidence that QAOA actually is doing something which may outperform other quantum algorithms out there and also other classical algorithms. On the other hand, for protein folding, it's quite a challenge to even solve small instances of protein folding problems. And it seems that based on our experiments, QAOA might not significantly outperform classical algorithms. So there's a couple of papers associated with this work you can read if you're interested. The first one is on the archive, and this is a joint work with Sami Bulibnan. This is the work on KSAP. And the second one was recently published in MPJ Quantum Information. And this is joint work with Sami and with a team at Roche who provided the expertise on the bioscience side. And that's everything I would like to say. And so I'm very happy to take any questions that you might have.
Thanks so much, Ashley. That was a very interesting talk. We do have a few questions from the audience, and I have some as well.
Sure.
So you find a scaling advantage for the random case set problem with QAOA. And I guess one question is, how sensitive is the scaling advantage to things that we know we need to do in a real device? So some error correction overhead, for example, or error mitigation overhead in the near term.
Yeah, that's a really nice question. And I think that it sort of really depends is the answer, because I think one thing that we know is that in theory, the overheads for error correction and fault tolerance are actually kind of lower order ones. Like they, might be sort of a logarithmic correction or something like this. And so another point, which is kind of an important one, is that the one thing that I think is interesting for applying QAOA to these problems is that actually the algorithm is quite low depth. So the number of layers of the algorithm might, this P might be, 20, 30, 50 or something. But in particular, it doesn't scale with the problem size n, at least not in the problems we were looking at. So because the circuit is much less deep than the sort of circuit which we need for Grover's algorithm, for example, maybe the demands in terms of fault tolerance are much less. So this is one reason why it's an interesting near-term algorithm. So I think it's an interesting question, and it's possible that even if there is a scaling advantage, some sort of practical costs like this would actually wash this out in reality. But sort of as a theoretical result, I think they probably will not.
I see. Great. Thank you. And we also have a couple questions regarding the protein one. Sure. One is maybe more technical. So how is the penalty term tuned, especially when you start to compare against like classical optimizers as well?
Right. And I think basically, we just have this one term here, this lambda, I think if I remember correctly, that we basically just searched over different lambdas, and it's just another thing that you can optimize. It's another sort of hyper parameter. But obviously, it's something that you can choose to sort of bias one way or the other. So if you want to have very few clashes, you have to have a very sort of, want to guarantee you have a physically reasonable solution, then you can really make this one very high and this penalty very high. And I think that in the results I presented here, we sort of we're looking at an optimal choice of lambda here. But I'd encourage you to take a look at the paper because this was a while ago now. But I think that's what we did.
Got it. Thank you. And so in that Hamiltonian, or the energy cost, right? We have Leonard-Jones and the number of clashes. Like, how do I guess in the poly basis, what does that look like really? Are these like Z and Z terms?
Right. So this ends up giving us something which is a bit more complicated than in the QAOA type example, because basically you need to do some kind of arithmetic here to be able to compute these things. So like this number of yes. So let me see. So that this also kind of comes into the choice of this encoding, right, that you use here. So to even determine whether you've got a clash, like from a sequence of turns in the lattice, it may not be totally obvious, right? You need to basically work out where you are on the lattice based on the turns that you've taken, and then you need to see, like, is there something else that's at the same position. So again, we have some sort of circuits for this, or algorithms for this in the paper, but it's another reason why I think this is going to be a challenge on a near-term device, because actually you need to do some calculation in order to compute these things. It's not just as simple as having like a ZZ term or something like this.
Got it. It's not like the encoding is not just like 0 or 1 state means clash or not or something. It's more complicated, and because there's some higher space that you're working in. That makes sense. And so you present, I think, this overall pessimistic view of being useful for protein folding. And I wonder if, like, how sensitive this conclusion is to making the problem easier or harder, right? Like, is it going to be more pessimistic or more optimistic? For example, you choose a particular term-based encoding. Maybe the Leonard-Jones potential is not sensitive to the type of the atom on the main chain. Lots of things that can be played around with. So do you think that what you presented here is pessimistic on the safer side, or like maybe more optimistic than the situation really is?
Yeah, so I think the answer is that everything that we did in this part, it's one small scale numerical experiment, and I think it's a very valid question, like how much we can infer about other situations. I think that there's two things I'd say. So I would say it may well be that QAOA will happen to perform better just with other encodings, with other particular sort of instances. But I guess I would also say there's somehow no particular reason to think that it should do especially well for these sorts of problems, just because the protein folding problem doesn't have any particular sort of structure to it that I'm aware that quantum algorithms can take advantage of. It's somehow not mathematically especially sort of tractable. And this was actually a nice aspect of this, this abstraction we were looking at, this self-avoiding walk one, because there, the problem is mathematically much nicer, and in fact, the performance of QAOA turned out to be a bit better for that. So I would say that, if one is an optimist about the performance of QAOA for these sort of unstructured optimization problems, then you shouldn't feel totally disheartened by this. But on the other hand, I don't think it particularly shows, positive evidence that QAOA will be outperforming classical algorithms on protein folding anytime soon.
Great, thank you. So we have one final question from the audience, more blue sky, I guess. What is the hope for optimization on a quantum computer if QAOA is not the one?
So, as a quantum algorithm designer, of course, that's a question that's sort of very close to my heart. I think that QAOA has some really nice sort of appealing features which make it a very tempting algorithm to think about in the near term. In the longer term, people have thought about many other kinds of quantum algorithm, in particular ones based around quantum walks or uses of sort of Grover's algorithm in clever ways. And if you have a fault-tolerant machine, then it may be that these actually do outperform classical algorithms, although there's been a lot of skepticism about this recently because of the overheads of fault tolerance and perhaps the relatively small speedups that are obtained. So that, I think, is one way, one sort of different family of algorithms that one could consider. And people have also thought a lot about sort of variants of QAOA and ways that you can sort of really generalize this part or that part to try to do better. But I think, yeah, the question of finding other near-term optimization algorithms that may beat QAOA, or maybe, you know, we can analyze theoretically more accurately, I think is a really interesting one. It's still quite open.
Got it. Thank you. Well, thanks so much for coming, Ashley. I think we're right on the hour. Perfect timing. And of course, a big thank you to all of the audience members who tuned in and asked these great questions and kept us all engaged and helped us dig deeper. So if you'd like to continue the conversation, hop over to the Qiskit Slack workspace. Like this video, subscribe to this channel, Qiskit YouTube, and we'll see you not next week, but in 2 weeks. Thanks so much.
Thank you.